Dry ice, sometimes referred to as cardice, is the solid form of carbon dioxide. It is used primarily as a cooling agent. Its advantages include lower temperature than that of water ice and not leaving any residue. It is useful for preserving frozen foods, ice cream, etc., where mechanical cooling is unavailable. Dry ice sublimes at a 78.5 AA degrees Celsius at Earth atmospheric pressures. This extreme cold makes the solid dangerous to handle without protection due to burns caused by freezing. While generally not very toxic, the outgassing from it can cause hypercapnia due to buildup in confined locations. Properties: dry ice is the solid form of carbon dioxide, comprising two oxygen atoms bonded to a single carbon atom. It is colorless, with a sour zesty odor, non-flammable, and slightly acidic. At pressures below 5.13 atm and temperatures below or 56.4 AA degrees Celsius, CO2 changes from a solid to a gas with no intervening liquid form, through a process called sublimation. The opposite process is called deposition, where CO2 changes from the gas to solid phase. At atmospheric pressure, sublimation deposition occurs at a 78.5 AA degrees Celsius. The density of dry ice varies, but usually ranges between about 1.4 and 1.6 gram per centimeter 3. The low temperature and direct sublimation to a gas makes dry ice an effective coolant, since it is colder than water ice and leaves no residue as it changes state. Its enthalpy of sublimation is 571 kilojoules per kilogram. Dry ice is nonpolar, with a dipole moment of 0, so attractive intermolecular van der Waals forces operate. The composition results in low thermal and electrical conductivity. History: it is generally accepted that dry ice was first observed in 1835 by French inventor Adrien Jean-Pierre Thaloria, who published the first account of the substance. In his experiments, he noted that when opening the lid of a large cylinder containing liquid carbon dioxide, most of the liquid carbon dioxide quickly evaporated. This left only solid dry ice in the container. In 1924, Thomas B. Slate applied for a U.S. patent to sell dry ice commercially. Subsequently, he became the first to make dry ice successful as an industry. In 1925, this solid form of CO2 was trademarked by the Dry Ice Corporation of America as dry ice, thus leading to its common name. That same year the Dry Ice Company sold the substance commercially for the first time, marketing it for refrigerating purposes. The alternative name cardice is a registered trademark of Air Liquide UK Limited. It is sometimes written as cardice. Manufacture: dry ice is easily manufactured. First, gases with a high concentration of carbon dioxide are produced. Such gases can be a byproduct of another process, such as producing ammonia from nitrogen and natural gas, or large-scale fermentation. Second, the carbon dioxide-rich gas is pressurized and refrigerated until it liquefies. Next, the pressure is reduced. When this occurs, some liquid carbon dioxide vaporizes, causing a rapid lowering of temperature of the remaining liquid. As a result, the extreme cold causes the liquid to solidify into a snow-like consistency. Finally, the snow-like solid carbon dioxide is compressed into either small pellets or larger blocks of dry ice. A teaching laboratory demonstration for the production of dry ice is to use a carbon dioxide fire extinguisher with a porous fabric collecting bag over the nozzle. The expansion of the gas lowers the temperature enough to produce dry ice snow that is collected in the bag. This is an inefficient process, and unsuitable for even lab-scale production. The expansion is inefficient, fire extinguishers are an expensive way to buy carbon dioxide, and there is the safety risk that extinguishers are left empty and not refilled. Dry ice is typically produced in two standard forms, blocks and cylindrical pellets. A standard block weighing approximately 30 kg is most common. These are commonly used in shipping, because they sublime relatively slowly due to a low ratio of surface area to volume. Pellets are around 1 cm in diameter and can be bagged easily. This form is suited to small-scale use, for example at grocery stores and laboratories. Applications: commercial. The most common use of dry ice is to preserve food, using non-cyclic refrigeration. It is frequently used to package items that must remain cold or frozen, such as ice cream or biological samples, without the use of mechanical cooling. Dry ice can be used to flash freeze food or laboratory biological samples, carbonate beverages, and make ice cream. Dry ice can be used to arrest and prevent insect activity in closed containers of grains and grain products, as it displaces oxygen, but does not alter the taste or quality of foods. For the same reason, it can prevent or retard food oils and fats from becoming rancid. When dry ice is placed in water, sublimation is accelerated, and low sinking, dense clouds of smoke like fog are created. This is used in fog machines, at theaters, haunted house attractions, and nightclubs for dramatic effects. Unlike most artificial fog machines, in which fog rises like smoke, fog from dry ice hovers above the ground. Dry ice is useful in theater productions that require dense fog effects. It is occasionally used to freeze and remove warts. However, liquid nitrogen performs better in this role, since it is colder so requires less time to act and less pressure. Dry ice has fewer problems with storage, since it can be generated from compressed carbon dioxide gas as needed. Plumbers use equipment that forces pressurized liquid CO2 into a jacket around a pipe. The dry ice formed causes the water to freeze, forming an ice plug, allowing them to perform repairs without turning off the water mains. This technique can be used on pipes up to 4 inches in diameter. Dry ice can be used as bait to trap mosquitoes, bed bugs, and other insects, due to their attraction to carbon dioxide. Industrial. Dry ice can be used for loosening asphalt floor tiles or car sound deadening material, making it easy to pry off, as well as freezing water in valveless pipes to enable repair. One of the largest mechanical uses of dry ice is blast cleaning. Dry ice pellets are shot from a nozzle with compressed air, combining the power of the speed of the pellets with the action of the sublimation. This can remove residues from industrial equipment. Examples of materials removed include ink, glue, oil, paint, mold and rubber. Dry ice blasting can replace sand blasting, steam blasting, water blasting or solvent blasting. The primary environmental residue of dry ice blasting is the sublimes CO2, thus making it a useful technique where residues from other blasting techniques are undesirable. Recently, blast cleaning has been introduced as a method of removing smoke damage from structures after fires. Dry ice is also useful for the degassing of flammable vapors from storage tanks. The sublimation of dry ice pellets inside an emptied and vented tank causes an outrush of CO2 that carries with it the flammable vapors. The removal and fitting of cylinder liners in large engines requires the use of dry ice to chill and thus shrink the liner so that it freely slides into the block. When warmed in place, the resulting interference fit prevents motion. Similar procedures may be used in fabricating mechanical assemblies with a high resultant strength, replacing the need for pins, keys or welds. It is also useful as a cutting fluid. Scientific. In laboratories, a slurry of dry ice in an organic solvent is a useful freezing mixture for cold chemical reactions and for condensing solvents in rotary evaporators. The process of altering cloud precipitation can be done with the use of dry ice. It was widely used in experiments in the U.S. in the 1950s and early 60s before being replaced by silver iodide. Dry ice has the advantage of being relatively cheap and completely non-toxic. Its main drawback is the need to be delivered directly into the supercooled region of clouds being seeded. Dry ice bombs. A dry ice bomb is a balloon-like device using dry ice in a sealed container such as a plastic bottle. Water is usually added to accelerate the sublimation of the dry ice. As the dry ice sublimes, pressure increases, causing the bottle to burst. The device was featured on Mythbusters, episode 57 Mentos and Soda, which first aired on August 9, 2006. It was also featured in an episode of Time Warp. Occurrence on Mars and Venus. Following the Mars flyby of the Mariner 4 spacecraft in 1966, scientists concluded that Mars polar caps consist entirely of dry ice. However, Findings made in 2003 by researchers at the California Institute of Technology have shown that Mars' polar caps are almost completely made of water ice, and that dry ice only forms a thin surface layer that thickens and thins seasonally. A phenomenon named dry ice storms was proposed to occur over the polar regions of Mars. They are comparable to Earth's thunderstorms, with crystalline CO2 taking the place of water in the clouds. In 2012, the European Space Agency's Venus Express probe detected a cold layer in the atmosphere of Venus where temperatures are close to the triple point of carbon dioxide, and it is possible that flakes of dry ice precipitate. Safety. Prolonged exposure to dry ice can cause severe skin damage through frostbite, and the fog produced may also hinder attempts to withdraw from contact in a safe manner. Because it sublimes into large quantities of carbon dioxide gas, which could pose a danger of hypercapnia, dry ice should only be exposed to open air in a well-ventilated environment. For this reason, dry ice is assigned the S phrase S9 in the context of laboratory safety. Industrial dry ice may contain contaminants that make it unsafe for direct contact with foodstuffs. Although dry ice is not classified as a dangerous substance by the European Union, or as a hazardous material by the United States Department of Transportation for ground transportation, when shipped by air or water, it is regulated as a dangerous good, and IATA Packing Instruction 954 requires that it be labeled specially, including a diamond-shaped black and white label, UN 1845. Also, arrangements must be in place to ensure adequate ventilation so that pressure buildup does not rupture the packaging. The Federal Aviation Administration in the U.S. allows airline passengers to carry up to 2.5 kg per person either as checked baggage or carry-on baggage, when used to refrigerate perishables. Notes and references. Notes. References. Bibliography, yours, Cal. Matheson Gas Data Book. McGraw-Hill Professional. PA 982. ISBN A978-0-07-135854-5. Retrieved July 27, 2009. Har Currency Ring, Heinz Wolfgang. Industrial Gases Processing. Christine Anna. Wiley VCH. ISBN A978-3-527-31685-4. Retrieved July 31, 2009. Trelow, Roy. Plumbing Encyclopedia. Wiley Blackwell. ISBN A978-1-4051-0613-9. Retrieved July 31, 2009. Houseecroft, Catherine. Sharp, Alan G. Inorganic Chemistry. Harlow, Prentice Hall. ISBN A0-582-31080-6. Retrieved July 31, 2009. Mitra, Somenith. Sample Preparation Techniques in Analytical Chemistry. Wiley IEEE. ISBN A978-0-471-32845-2. Retrieved July 31, 2009. McCarthy, Robert E. Secrets of Hollywood Special Effects. Boston, Focal Press. ISBN A0-240-80108-3. Duane, H. D. Roller. Thalloria, M. Thalloria and the First Solidification of a Permanent Gas. ISIS 43, 109 113 doi, 10.1086/349402. JSTORA 227174, Kanner, S.K. Kapala, Dr. B. Comprehensive Chemistry X Laxmi Publications. ISBN A978-81-7008-596-6. Retrieved July 31, 2009. Gurol, Alan H. Mully, Albert G. Primary Care Medicine, Office Evaluation and Management of the Adult Patient. Lippincott Williams and Wilkins. ISBN A978-0-7817-7513-7. Keyes, Conrad G. Guidelines for Cloud Seeding to Augment Precipitation. American Society of Civil Engineers. ASCE Publications. ISBN A978-0-7844-0819-3A.